If we look at the top of draw, we clear the screen. And then of course we set our sprite batch begin because we're about to use sprite batch to draw something. And then here we are doing two loops, one inside the other. A two-dimensional loop, which, not coincidentally at all, is designed to walk through a two-dimensional array. We have a two-dimensional array, it's our landscape, so using this for loop for the map height and for loop for the width inside that, a nested loop allows us to touch or at least look at and do something with every single element of our two-dimensional array. And what are we doing with every single element of our two-dimensional array? We ask a simple question. If it's 1, then we draw the wall. Otherwise, we draw the grass. And what's going on here? X times 24, Y times 35. Well, if we have a chance, and I think we do, we can go over here to grass.png, double click it, and it fires up the paint, the normal Microsoft Icky Paint program. And we can hopefully scale it up. No, we can't. It's an Icky Paint program. Oh, here's a magnifying glass. That's what I wanted. So this tiny little hunk is the grass, and if we move our mice to the right position, it says they're 23 by 34. So if we go one more to the outside of it, is 24 by 35. So 24 wide by 35 tall is this particular little grass image. In fact, it happens to be the size of all 4 of the little gritty square pieces of art that we're using for this game. So, and that's good. It's good to know that that's how many pixels high and how many pixels wide each game cell is. Now, this is not the only time, in fact, there will be many times in your video game career where you will be working in 2 spaces at once. You'll be working in pixel space and you'll be working in cell space. When you have an array, 2-dimensional array of things, of places to go, dungeon walls and corridors and rooms to explore, those are all in the space of whatever dungeon map you happen to have built. That's separate from pixels and the pixels on the screen. But it gets kind of confusing because pixels on the screen also happen to be a 2-dimensional array with X and Y position values. So getting into that, understanding that there's a 2-dimensional array of pixels that you're drawing on the screen and that you're using art with, and also separately there's a 2-dimensional array representing the world that your game happens in, is sometimes tough to get into, and it takes a little practice. But that's why we're here, to learn and to practice. And in this case, this is our translation between pixel space and cell space. The pixels, there are 24 pixels wide in each cell, and there are 35 pixels high in each cell. That's why we're doing this multiplication, because X and Y, as you can see, are firmly in cell space. They represent the cells of our 2-dimensional array. They don't represent pixels at all. We have to translate them by multiplying them by the width and height of each cell to get to where we want to draw them on the screen. So here's this code. It draws our map. And it's the first thing we draw because it's the bottom thing we want to draw. We want to draw things underneath it. Now we're drawing the wizards. So what are we doing? We have a for loop, and it starts at wizard start, and it ends at wizard end. We already know because we can go back up to the top of the program and find out that wizard start is 1 and wizard end is 3. And because it's a constant variable, it will always be so for the length of time that our program runs. We like that. So we come back here to the draw function from 1 to 3 of the list, that is to say the wizards of the list. We make a couple of variables that are our X and Y cell of our wizard, and then we use those times 24 and times 35 to draw the wizard art. So here we're drawing all of our wizards. Now the comment down here, of course, says I want to draw the player last because I would like the player, the knight, to always appear on top of whatever wizard is also standing in the same square. It makes things less confusing for the player, right? Especially if they're they're controlling the knight, then they need to see what they're controlling. So I could have theoretically drawn the knight and the wizard all in one loop. But in this case, I drew the wizards first, and now to make sure that the knight always draws on top, I will draw the knight separately. Content knight, and notice I'm using player start, which is 0, as my object X array and object Y array indexes. After I've drawn the map, the wizards, and the player, I'm done. So I'll do sprite batch end, and I'm done with the draw function. So sweet, we know now that all of the wizards and the player take a turn individually. But we also know that they all kind of just belong to a long one-dimensional array of X and Y. And there's not really all that much difference data-wise between wizards and knights. We happen to have one knight, we happen to have 3 wizards, but that's actually kind of arbitrary. That's what we decided on. It's not something that's critically built into the code. We could change it to 5 knights and 10 wizards if we wanted to. It wouldn't be hard. We just changed the numbers. I'm looking here at a function called CanGo. And it's actually hard to understate the importance of this function. When we program video games, we, again, often work in a 2-dimensional world space. We often work in a game where we have X and Y, corridors and walls and doors and a floor, and everything's in a regular 2-dimensional grid. It's how so many games have been made. And traversing that world starts out as simple as, is there a wall in front of me? And if there is, I can't go there. Otherwise, I can go there. But it quickly gets pretty complicated. I mean, when you put in doors, when there's a monster blocking your way, oh no, there's a pit. Does it block your way or do you fall to your death? Suddenly, the issue of where you move and how you move and can you move gets kind of complicated. And it especially gets complicated because your wizards have to make that determination, and the player has to make that determination, and practically anything else in the game has to make a decision. Can I go here? So having a single central function called something like, say, CanGo starts to make a really nice amount of sense. So we've made a CanGo function here. It's very useful. Let's explore it real quick. It's not actually very complicated, but the cool thing about the CanGo function is that we can make it more complicated over time. And it keeps us from making other parts of our code much more complicated. So here's our CanGo function. You can see that I pass in an X and a Y. That's the cell location that I'm asking the question. Could I go here? So it's not where I'm standing now. It's where I want to go that I'm passing into the CanGo function. CanGo returns a bool. That's a Boolean. That's a true or false statement. It can only be true or it can only be false. It can't be 5 or 13 or 256 or some string. It's always just 1 or 2. And in this case, that works perfectly for CanGo, because when you call the CanGo function, you're looking for a yes or no answer. Can I go there? Yes or no? So in CanGo, we start to say, by saying a simple test, are the X and Y values outside of the map you're on? There's no way you could go outside of your own map. I mean, unless you're some sort of Tron genius thing, but that's not what we're programming here. So no, if your values are even outside of the bounds of the 2-dimensional array which represents our map, no, the answer is you cannot go. The next thing we test is real simple. We look at the map array and check y comma x and say, is this square equal to 1, which means wall? If that's true, no, you can't go there. Return false. After all is said and done, the only logical thing left is that you can go there, so return true. So it may seem a little pedantic, but believe me, I remember the revelation when I discovered the use of a CanGo function and how much it cleaned up my code and made things much more sensible for me. So I'm a hearty fan of a can go function, and in any two-dimensional grid-based world, like say Pac-Man, I think that you can't get along without a can go function. So let's look down here. We've got a couple more functions: check player input and move wizard randomly. So let's look at move wizard randomly. Remember that this is the code that executes when the turn timer counts down to 0 and it's the next wizard's turn. So what happens with move wizard randomly? Well, first off, we pass in the argument of the wizard index. In other words, which wizard are we talking about? Well, that's that. Wizard 1, Wizard 2, or Wizard 3. First thing we do is we set wizard has moved to false. And then we loop until it's true. Because we're gonna keep looking for a place for the wizard to move until we found a good place for the wizard to move. And this is a pretty good choice when you're moving randomly, because when you have a can go function and you move around randomly, you quickly realize that there's plenty of situations where the can go function will return false. You'll try to move into a wall randomly, you can't go there. What do? Well, you could skip your turn. You could say, well, I tried to move into the wall, but I couldn't. I guess I'm done. And that's not unreasonable, but sometimes you want the wizard to appear to be a little bit smarter, so he wouldn't even try to go into the wall. So in this case, if he tries to go into a wall and he fails, he'll try again. He'll try some other direction. That's what this while loop is for. So now that we have a while loop that goes through until the wizard has moved, first thing we're going to do is this transfer of data from object X array sub wizard index and object Y array sub wizard index into dx and dy. So this is us saying that dx and dy is the current position of the current wizard. And then this code here changes dx and dy by 1 in one direction. So this is where we randomly figure out whether we're going north, south, east, or west in these lines here. And then of course, since we found the place we would like to think about going, we call can go. And if it's true, if we can go there, then we'll take the dx and dy new positions and put them back in our actual object array values. This is where we actually do move the wizard. And then finally we set wizard has moved to true, so that the next time through the while loop we're done and we don't do that anymore and we get out of this function. This is all well and good, but if you do a few more things, you might run into a problem. Because you have a while loop and the while loop keeps going until the wizard moves, we have a potential for an infinite loop if the wizard has no place they can possibly move. Now right now there's no collision between wizards and other wizards or knights, which means that multiple wizards can share the same space. If we stop that, then you could imagine a wizard walking into a blind alley, and then another wizard walking after that wizard, and then the first wizard kind of gets trapped between 3 walls and a wizard and has nowhere to go. If that's the case, then you have a potential of your program kind of hanging up and never getting out of this loop. And there's different ways to deal with that. It's not too hard, but it's something that we have to pay attention to. So that's the entirety of the move wizard randomly function. Now we're going to look down here at check player input. Now, move wizard randomly just tried to make a decision about which way does the wizard go. This check player input function pretty much does exactly the same thing, except that instead of choosing a random path, it looks at the keyboard and tries to detect whether the player chose a path by one of the pressed buttons. Here in move wizard randomly, we take the variables that represent the x and y of the wizard and move them into temporary variables called dx and dy, and then at the end we move them back. Here in check player input, we do pretty much the same thing by making 2 new variables called player x and player y. And again, we do this for sanity's sake and also to make sure that if we modify these variables, we're not necessarily modifying the original variables and the original data. So, after we've set player X and player Y to the current location of the player, we check, is key down left? Is it? Well, then we're going to say, can go to the left of us? Yes. Then two things happen. We actually move player X to the left by saying -1, and we also set turn timer equal to 1. So what do we do here? Turn timer equals 1. What we're doing with turn timer equals 1 is we're setting the turn timer back so that it can count down to 0 again, so that it can then move on to be the next wizard's turn. But as long as that doesn't happen, as long as turn timer equals 0 and stays at 0, we're still kind of waiting on the player input and nothing else happens, and the wizards can't take their turns until we've moved. So in this piece of code here, where we check a key, we check can go, and if both of those things are true, then we move, is repeated for the left and the right and the up and the down. And then finally, after we've gone through these 4 bits of code, we have one more line that simply says, if turn timer is 1, that means that somewhere along the line we pressed a key. And if we pressed a key, then those temporary variables, player X and player Y, need to be put back in the position of in the actual position of the knight. So there it is. We have a function called check player input, and it just does what it says. If the key is down and you can go there, then we move the knight and we set it up so that it's the wizard's turn next. Above that, we have our move wizard randomly function, which for each wizard keeps trying in a random direction until it can move somewhere. The important can go function is where we put all of our actual checks to say, could we go there or not? The simple can go function just returns Boolean, true or false, can go or cannot go. And our draw function and our update function. So if I hit F5 again, you can see that I can move my knight around because it's my turn. And when my knight is moved, it goes through and takes a turn for each. In the end, all we've got is a knight and some wizards moving around. But more than that, we've got the basis for a whole lot of games. I mentioned Pac-Man before. Pac-Man is a very cell-based game. It may look like Pac-Man is moving smoothly through the maze, and so are the ghosts, but they're moving in a grid. They're moving in a two-dimensional cell-based world, and they're making decisions that are basically the function can go. So the smoothness of the characters is really about just applying the timers to the positions of the Pac-Man and the ghosts. There are so many games that express themselves in a two-dimensional grid and have objects that move around and interact with the simple world. This assignment I consider to be one of the most fundamental and important assignments I can teach. This idea about cells, that is a two-dimensional grid that we make in our game, might represent a level, and there's traversal of that level. There's units moving around inside that level, and it's important to understand how they move around inside the level. But it's also very much important to understand how we draw that level and how we recognize the difference between a two-dimensional array of pixels, which we're drawing on the screen, and the two-dimensional array of cells which represent our game world. They're different, and yet they're slight. They're kind of similar. So we got to keep it straight, and sometimes it's confusing. As always, when I give you a piece of code that works and as a baseline, a support platform, I certainly expect you to build on it. I want you to explore it and do your own thing with it and find out what cool games you could create using the simple building blocks that I gave you. In this case, let me give you some ideas, as usual, for how to go about doing that. Number one, you could add more wizards. That should be pretty trivial. You only have to change the values of the const variables near the top of the program. You could also add more knights. And of course I would expect those knights to be controlled by the player. Another thing you could do easily is change the size of the maze. That requires more changing of constant variables, but you also have to change that two-dimensional array at the top of the program that was expressly defined. Also, you could change the layout of the maze. Right now the maze is not actually very complicated. It could be a lot more complicated. Again, if you've ever seen a game like Pac-Man or any other kind of maze game, you could realize the possibilities of how mazy a maze can be. So how about this? You could add a new object and a new piece of graphic to the game. You could add a door. The door would be neat because the knight could move into that space and the wizards could not. Now suddenly you're thinking, wait, that's a change to the can go function. But that's the cool thing about the can go function. It's designed to be changed as you need it to be changed. In this case, it would look at a door and say, am I a wizard? No. Am I a player? Yes. Aside from a door, there's plenty of other cool graphical tiles that you could add to the maze that would affect the knight and or the wizard in fun ways. And how about more enemies than just wizards? Every dungeon needs a dragon, right? That'd be cool to put into the game. So of course, we've got the knights and the wizards moving around, but they're not actually interacting with each other. Wouldn't it be nice if we had the wizard die, go away, when the knight moves into the wizard space? And how about if a wizard moves into the knight space, then the knight dies and the game's over? That'd be an interesting thing to add. Here's something we expect wizards to do. We could make the wizards randomly, occasionally teleport. We've already got a random number generator in our code, and can go works just fine even if you're not trying to figure out whether it's one space away from you. So why not a teleporting wizard? Now collision is another thing that you eventually have to get into, and whether you use can go for this or not, making wizards not stand on each other's bodies sounds like a pretty neat idea. Let's make it so that the wizards don't walk into each other's spaces. So you notice right now that the knight moves left, right, top, or bottom, and nothing happens until the knight moves. But if you really are building a kind of a tactical game, it's very frustrating for the player. So giving them an extra option, like maybe the space bar, to let them skip a turn and not move might be really neat. Now here's a cool one. We all expect wizards to cast magic spells, right? So it'd be more complicated, but I'm certain you could find a way to make the wizards cast Fireball on the knight. And finally, how about sound? You've put sound into previous projects, so why not add sounds? People stomping around and knights clanking and wizards firing fireballs. That'd be loads of fun. Alright, I hope that you've learned something, and I hope that this does its job of teaching, and I hope that you're excited about the possibilities with this assignment that I've given you. So have fun, and see you next time.